have a small chance in the struggle. Now, I read the pleasure of introduce you, Professor Sarkis from Westchester Institute.
Worcester, yeah.
Okay. So let's here. I have no title here at the moment. So let's.
Okay, thank you. Thank you.
Sarkis is honorary IMPA. That should make it clear. He's been here for a number of years, and we all know his contributions.
Okay, thank you, Dan. So let me thank you for the invitation. So let me tell you how I met Dan. Okay, so my undergrad is in
Always knew you.
aerospace. No, wait. My undergrad was in aerospace engineering. So I was working at Petrobras, like 15 days on the offshore, 15 days doing nothing, right? So eventually I started getting a little bit upset with doing nothing. And then I started going to university to see if I can do something between, right? And then I went to PUC, and I found a very beautiful flyer. I don't know if you remember this flyer, doing some advertisement about petroleum engineering, mathematics, or modeling. I don't remember the title. And there was a very nice group like Patino, Flávio, PJ, you, of course. And then I apply, okay? PJ, okay? And then I apply, okay? So engineering from Petrobras, getting maybe 20 times more than a fellowship, right? So it's a little bit weird. And then Dan saw our application and he invited us, me and my friend Luis Langoni, to his house. So Dan was the first high caliber mathematician I met at that time. Okay, so I went to his house, he interviewed us, etc. So we got the fellowship.
That's what you mean, right?
Yes.
High caliber.
Yes.
Understand.
Yes. And basically that's how I started doing. So I went to PUC. So I got PUC, then left to IMPA. Okay. So and then I said okay. And then I started to work with Carlos Tomei. I finished my master, and then I moved to Courant, maybe to work with Glyn, but Glyn left. Remember? So anyway, so at the end I started doing something completely different, real numerical analysis, things like this. So, and the second door that Dan helped me was to come to IMPA. Okay, so I was at Boulder, I moved to WPI, and then I got this invitation from Dan and André, and then I moved to IMPA in 2001. Okay, then I spent maybe 12 years here, half of these 12 years full-time. So I had to leave because of some personal problems, but I'm really, maybe I never told you, but it really changed my career. Okay, otherwise I would be probably an engineer. Okay, so I don't know if it's bad or not, but I like what I'm doing. Okay.
Give me 1 second. I don't know with whom I was talking about the fact that there are few applied mathematicians in the market, and there are even fewer numerical analysts. There are really very, very few. He is one of them. And of course, he does not work only in numerical analysis. He does not only prove convergence of numerical methods. He uses them. He goes to the physics. He is actually an accomplished scientist.
Okay, thank you. So I came here, and then I imagined, like, what can I talk here? Because I'm not. In fact, I wrote one paper with Dan in how to use Riemann solvers to a Godunov scheme, things like this. So anyway, so now I felt like, what can I talk in this conference here, right? So basically, the most hyperbolic problem I've been working with is this one. You're going to see that's not so hyperbolic, but there is a second order wave equation there, right? So there are subsonic regime, okay? So the problem that I'm going to model is crack propagation, Okay, so I'm going to show some pictures later and also the move. But before, let me tell you what crack is. So if you take some elastic body, you're going to see that there are three modes. Okay, the first mode is called, I'm going to start with the mode 3. Okay, the mode 3 is basically to do this. Okay, you cut like this. So basically, also you can think like this. You're here and do this. Okay, so the only movement is what you call the U3. Okay, so this is the mode 3. Okay, the mode 2, the mode 1 is to do this. I have the crack by open like this. Okay, so you see that this kind of mod you need to work with 2D vectorial fields. Okay, and the mode 2 is to do like this. It's like this kind of things. So there are modes like this, and this. Okay, this talk is about in this direction, U3. Okay, this is like hitting the window in the normal direction and avoid all the deformation in the plane, just in this direction. Okay, so the first, I'm going to show a movie. I'm not so good in this. Basically, this is like I'm open like this. Okay, you see that you're going to see in the next picture, you're going to see that there will be bifurcation. Okay, so let me play again. So this is the U, how much is deforming. Okay, it breaks, it's going to break again, and you're going to see in the other picture. So this is, you call the U, is the displacement in the vertical direction. So let's go to another movie here. So that's the only, I have just two movies. Okay, so this is like, is to have an idea what's happening. Okay, this is the V variable that I'm going to define soon. And that's what the kind of model you want to do. Okay, so you're going to see two bifurcation here. Okay, so this is the crack. So our crack is going to be not a sharp crack, but something is moved. Okay, that's what's called the phase field. You have a second crack. And this starts cracking, cracking, cracking. In fact, I can adjust the parameter to have a much more drastic. So let's go to my talk. So here is Alt, Control. No. I don't know how to do here. Oh, excellent. Okay. So this is a joint work with Chris Larsen. So he's an analyst. So he's the one that knows more about these fields, the modeling. And our postdoc, Malika. Okay, so he is the one that is doing all the computations. Okay. So this is an example of a crack. So example, take the window, so do some slit, right? And then you start open like this. Okay, so it crack once and then you start cracking. Here, start cracking. So you see that this is a crack type mode 1. Also, normally the 1 and the 3, the 1 and the 2, they are together.
Is this how the cell phone glasses?
Yes, that's another. Yes. So you see the crack comes here, it bifurcates. So you're going to see this bifurcation here. And then keep going, bifurcate again. You're going to see a second bifurcation. And this keep going if my domain is infinity. You see that here, in order to capture very well the deformation, because it's very high stress, you need to do refinement. Okay, so how to do the refinement? You don't know where the crack is going to be. Okay, so that's the difficulty. It's like you don't know how to crack where the crack is. In fact, it's possible if you put some special loads that the crack is initiate some place in the middle. Okay, it's possible. In fact, this happens. Okay, depends how you do your forcing term. Okay, so basically, I'm going to describe you what's the idea of the phase field. Okay, And then if I can just explain you what's the model, I will be happy here, okay? So basically, you have a body. You have a crack here that could be in 3D, so this is going to be two-dimensional manifold. Okay, you have variables like deformation. This is the strain, the grad of U plus the grad of U transpose average, and the stress, okay? For us, everything is going to be linear here. Okay, and there is this criteria by Griff, 2021, a long time ago. And the idea basically is like this. If you want, suppose you put some load here. Okay, if you allowed things to break, the energy is going to go down. And the reason is because your space gets larger. Your minimization space gets larger because you allow discontinuity. It doesn't need to be continuous there. So the energy, the strain energy, is going to go down. But there is a penalty term to allow this. And the penalty term is to cut the bonds of your material. Okay, so if you want to crack, you have to say how much energy you are going to spend to cut those atoms connections, okay? So this is the criteria. So let me give you the energy. So the energy basically is going to be the stiff energy of the material plus the length or the area, depends which dimension you're talking with. And basically if you're interested on working just with the static case, you just minimize this with boundary conditions, okay? The problem is that you don't know where gamma is going to be, because you can start with omega that has no crack. You put some loads and it cracks, but you don't know where it's going to be. And so that's the difficulty of the numeric scheme. How are you going to do a numeric scheme that I don't know where the interface of the crack is going to be? Okay. So basically, so this is, in fact, this kind of technique revived by when Gilles and Marigot, they introduced this concept that, in fact, it comes from Ambrosio and Tortorelli. Okay, and basically he started using this for image processing, and then the people started doing this for elasticity. So what's the idea here? The idea is to introduce a new variable, v. Okay. Now the integration is going to be in the whole domain. My space for u and v is going to be continuous, h1. Okay. All right, so the wife of Dan, if you don't know. Okay. And there is an extra term here. I'm going to describe what means those terms. Okay. So just for you to remember, v is going to be 0 at crack and 1 at, let's say, half region. Okay. So if the material is very nice, nothing happens with the material, v is 1. If it broke, it's 0. My v is going to be something between. Okay. So what's the idea? The idea is like that. I'm going to introduce AV. So just have in mind that AV is v squared. And just have in mind that this thing here, there are many choices. I'm just show you a few ones. It's going to be 1 minus v squared. Okay. So the idea is like this. If I make this v to go to 0, okay, you are going to see that there will be a coefficient here that is going to be very small. Because this is going to be very small, you are going to allow the gradient to be very large. Okay. But at the same time, you want to put something that somehow is going to measure the length of this crack that's defined by v. So it's very difficult to, because you don't know what v is going to be, so it's very difficult to find this length because you are not going to see. So the idea is to put some v that's going to be like this. In fact, it's like this. Okay, and if you compute this integral, it's going to give you exactly the length in a smooth way of this crack. Okay, so the idea is like that. See that this quantity here, see that epsilon is going to be very small. this quantity here wants V to be equal to 1, the half region. Okay? But V wants to be 0 here. Okay, and so you put this gradient here to avoid discontinuity. Okay, so your V is going to be smooth, it's going to be in H1. Okay, so this is basically the idea that introduced by Ambrosio, that he replaced that one that you have to put omega minus gamma, that's very difficult, to something that's everybody is going to be in H1. So this is going to be H1 of omega, H1 of omega. Okay, when epsilon goes to 0, Ambrosio showed that this is going to converge to the integration of omega minus gamma, and this is going to converge to the length of gamma, okay, in a gamma convergence way. That's the kind of convergence they are. So there are some analyses. So Blaise, Cruz, and Richardson, they made some dynamic model now. So that's their contribution. They introduced some how to do now dynamically. Okay? So basically they introduced this equation here that basically is ma is equal to F. Okay? The Newton law, like the variation of the momentum is equal to force. Okay? So that's how U is going to move. Okay, so basically because what they're doing is like this. Suppose you have a lid here and you want to see what the crack is going to do. So basically you put this up. So a wave is going to propagate here. You put this down, a wave is going to propagate here. So when they get close to this tip, it's going to be a huge stress. The gradient is going to blow up. The V is going to go down to 0. Okay? And the other term is to measure the length of this crack. You see that this kind of formulation is very nice because it doesn't matter if it's 1D, 2D, 3D. It's the same formulation. Okay, you don't need to worry much about mesh, aligning, discontinuity that you don't know in advance. Okay, also it allows you to start a crack in the middle of the domain. You call initiation. Okay, so basically the other equation that I'm going to do is a wave equation. So it's hyperbolic in this sense, so that's everything here is going to be subsonic regime. Like maybe it'll be interesting, since there are many shock people here, what happens if you go above the speed of the sound of the material? So what's going to happen? I have no idea. Okay, you are the expertise on this. So this is I never see people doing this kind of things, and also I don't know if it makes sense. Okay, so basically Chris Larsen with Zulli and other people, basically what they did to prove some convergence for the continuous in space but discrete in time is to discretize this in time using some back Euler, but they introduced this dissipation here. So that's how they could prove things. Okay. So basically what they're trying to do now is to put a discretization in space here, discretization in time here, get rid of this term, okay, because it's a little bit fake to prove results, and basically let me tell you what's going to be the algorithm, what's the idea. Okay, so this is the equation you have. Okay, you give some initial conditions, u and the velocity. Okay. And suppose you have the solution at time equal t. Okay. So basically I want to know what is u at t plus delta t. I solve this equation here, that's the second order in time. So the kind of scheme that uses some Newark kind of schemes. I don't know if you're familiar with this, but there are many versions of this. Okay. There are better ones, like if you see Tom Hughes and other people that does a lot do some stability analysis of structure, they use this kind of schemes, Newark scheme. So that's how you move u. Okay. Now, once I move u, I have to tell how I move v. So basically, the way to move v is to minimize. So let me go back here to to this one. So I know what is u here. So basically what I want to do here is to minimize this in v with this new u. And then I minimize. So this problem is not so easy as you can imagine, because comes this condition here, the crack reversibility criteria. This means the following: once you create a crack, you cannot go back. You cannot heal the crack back. Okay? So I have this condition of the v that if I go to some t plus delta t, the new v has to be smaller than v. See that v going down is when the crack is initiating, but you cannot go back. V cannot get larger than this one. So this means that the problem that I minimize is a minimization problem with a constraint. Okay? So that's the two-step: a wave equation, second order in time, and some minimization with constraint. And you start doing this time step. It's like where's the Braille? It's like a splitting time scheme, kind of. I'm not going to get in detail. Then you do some finite element. You multiply by a test function, the wave equation, integrate by parts, blah, blah, blah. The same thing is here. Everything is in H1. Don't need to worry about the crack. And basically, I transform the problem to a discrete one, because I introduce finite element. If the people want to do finite differences, okay. Okay, so I'm a finite element person, but I have no problem with finite difference. Okay. In fact, finite difference is getting so close to finite element nowadays. You can discuss about this. You know, there are new books by Cruz. There are many people that they show how to analyze finite difference, going back to finite element without imposing some regularity on f. F doesn't need to be in C4, these kind of things. So the kind of regularity basically is the same one as you do in finite element.
The fun of arguing will disappear.
Yes. Okay, so this was very hot in the past, but nowadays the people realize that they are very similar if you do it right. Okay. So this is the kind of numeric scheme. I'm not going to get in detail, but the most important thing here, there is this n here. So this is the mass matrix. Because it's finite element, you have to integrate phi I with psi j. So if you do finite difference, this is going to be identity. And this depends on v, because this is v squared grad u grad v. So this is changing. So things get more difficult to analyze. Okay. Now you need to minimize. I'm not going to get in detail here, but there is an algorithm based on the work by these people there. Okay, so I'm going to skip all this. Okay. So how I am in time? Okay, so it's going to take 5 minutes here. Okay. So now I need to tell how I'm going to refine the mesh. Okay, there are many criteria, because of course near the tip of the crack I like to have a very fine mesh. Also, think like that I have the crack, the solution is going to do like this. The wave is coming here, it's coming here, so the solution is going to have a big discontinuity here. Okay, so I like to have a very fine mesh there. So I want to have a very fine mesh there, and also on the tip, the place that they are creating new v's equal to 0. So basically, use the gradient of UH and V also, but the most reliable one until now is just look the gradient of UH. See that this is not exactly the stress, because the stress you have to multiply by the V square grad of U. So sometimes the people call this critical stress. Okay. Remember that near the crack, the stress is going to go to 0 because it breaks. All right. So let me show you our last pictures. Okay, this is our initial mesh, and then it evolutes in time, and you see more or less how it refines. Okay. Using that criteria of the grad of U. This is a picture of V. This is just V. So the red column means 0. the blue color means 1. So that's the kind of, and the thickness of this depends on the epsilon that you choose. The mesh that I choose certainly has to be smaller than epsilon. Okay? So that's the picture you get. By the way, we are using Dirichlet here. Neumann, and Neumann. Okay, it's like having a window, like a glass. You let free here, but here you do this. Yes. Okay, and there is a crack here that you didn't plot. Okay, this is the initial slit crack that I put here. I just put the new ones. Okay. This is a zoom. You see that they want to maybe start a new one here. And of course, this depends a lot of the bound condition that you impose. So basically now you're in the stage of, so the code works. It took a lot of time to make it to run smoothly. If I allow them, so by the way, there are many questions like, what's going to be the speed of the crack? Okay, it's going to be the speed of the sound of the material. In fact, what you see in reality is like, it's going to be like 0.6 of the speed of the sound speed of the material. Okay, questions? 0.6. Okay, you never go to 1. It'll be interesting if you really another thing that happens like that, you have to do this. If you do too fast, the code breaks because the velocity gets larger than the sound speed. So you go to this kind of shocks that is not in the modeling. So it'll be interesting if anybody here is interested on the supersonic regime. So why it bifurcate? Okay, why? Okay, so you can imagine like this. The crack goes, it increases the velocity, the stress start accumulate here, gets higher, event, dividing in 2. So you want to understand this mathematically. By mathematically, I mean, I want to go to here, transform this problem in a complex variable, and try to see where the big stress are. And this is going to give you the angle. Why this angle here is 60 degrees, things like this. You like to understand this kind of thing. So you've been working with this. What exactly speed of the crack thing is going to branch? And to finish up here, basically we just did like the mode 3. You like to do, the next step is to do this one here, is to do, where it is to do 2D, just the formation in this direction here. Both modes 1 and the one that does this, okay. Of course, I'm sure that a lot of people will be interested in the last topic, hydraulic fracturing. Okay, this will be outstanding work to do. Okay, this is not just for one person, okay, or two. You need a group. Okay, so this is very interesting. Okay, so there are some people doing this, like Mary Wheeler, especially, but somehow I don't understand what they are doing. It seems a little bit, it's like take some average of Stokes and RC. So it doesn't make sense in terms of modeling, okay? I've been talking with some people like Mike Ortiz from Caltech, that's a real material science person. So he said that this is not right. Okay, the right phenomena is, for him, is like this. You have a porous media down there, a lot of compression because of all the earth here. So basically, why the crack starts there? You start pumping. The pressure goes higher. Eventually, this pressure is going to balance all these columns of pressure that is pushing down. And then they start sliding. So this is the kind of phenomena that he thinks that that's the right way to do. Okay, so this is, for us, is mode 2. So now it's not like you have something here, you move the pressure and then it opens up. It's not this because the porous media is connected. So it's not like, you know, if the porous media is connected, the pressure, in other words, so There are better ways to do, in my opinion. I think that's a way to go. So I'm introducing this because maybe that could be a good topic for some people here. And basically, that's what I have to say. Thank you.
Near the crack, then it kind of opens in a stable way, and if you force it at a large distance, then it's unstable. It's like boom.
You know, there are many. If you go to a computational mechanics engineering conference, you're going to see half of the talks are going to be about crack. Okay, it's huge. It's huge. Okay.
But this approach is kind of universal.
Yeah, this is universal. Of course, the engineers criticize. Right, because it's phase fields. So, example, sometimes you see people make some complaints about thermodynamics. It's like this looks a little bit fake, gamma convergence, these kind of things. So, some engineers they complain because they think that this kind of modeling doesn't satisfy certain thermodynamic laws. Okay, and if you go to this conference, you're going to see people work on the tip, if the tip is like this, if the tip is like this, if the velocity of the tip should be in the model of this, because here you don't put the velocity of the tip. Okay, so it's huge. Okay, it's huge. So the advantage of here is that you don't need to worry about meshing. Just refinement. That's much easier. You don't need to find a mesh that aligns the interface to the tip, where it should go here, here, here. How you are going to do initiation, okay, of a crack that's... So it's, of course, every time you have something a little bit different, I'm not the one that started this, okay, there will be a lot of fights, right, so, but it's easy. You can do it in 3D easily. Imagine how to do fraction in the real one, the sharp one you call, in 3D. It's pretty difficult.
Off the top of my head, you asked about crack propagating too fast. Do you suspect what happens?
I don't think it's going to pass the sound speed, except if you force somehow.
And
Example, take like a samurai,
sword?
and very fast, faster than the... Of course, it's going to run, the crack is going to run faster than... So this is very artificial. Another way is like when you do this, we don't know. Maybe that's a good question. So what's going to happen if you take the samurai and go faster than the sound speed?
Elliptic region.
So this is for you guys, for the young generation maybe. It's like nobody, I've never seen anybody doing above the sound speed. But this is tough, I mean, you know.
Yeah.
You can imagine that this is not for
You don't do tough work, you don't know. You do nothing.
So I think this is a good topic for the young generation. Okay.
Thank you.
Pleasure.
Sarkis, do you know if there is some application of this model to tsunami formation?
No, I don't know. But it's like I saw the talk by the guy that talks about the Einstein equation, right? So it's like in his model, right? So maybe, I don't know if you thought about using phase fields because you don't need to know where gamma is. You see, so maybe it's a way to deal, I don't know, I'm just speculating. Okay. Yeah. So phase field is like, sometimes the people are afraid because it looks a little bit artificial, no properties, but there are a lot of properties. Okay. You have gamma convergence, the people use for image processing. Okay. Heavily. In fact, this starts with that function that I showed to you is basically the Mumford-Shah functional that you minimize to find contrast of pictures. Okay, so basically Ambrosio, he introduced the phase field and proved gamma convergence. Okay, that's beautiful. Doesn't mean that solution is unique, but you prove that the solution exists. It's really remarkable, in my opinion.
So,
Thank you.